The xenon difluoride. Okay, the gas phase diagram. Okay, so after the surface micro machining, actually we got to find some way to do the testing if the fabrication is successful, especially for the stress inside the material, inside the structure. So you want to do the testing quickly because it's quite small in a small area, and you want to do very sophisticated, very complex machine to do the testing. You can consider to design some testing structure on the wafer to do the testing. For example, you can do the many cantilever beams with different length, not cantilever, sorry, bridges, the bridge structures with different types of length and also the width. Okay. So so when you have a different cantilever beam, okay. So under this kind of compressive, because polysilicon is a compressive stress, right? So after you release the bridge, the underneath material has been taken out. The compressive stress will try to push the material. If the structure is not strong enough, so the structure will be bulking up to form. So after release, so this is polysilicon if it's a compressive stress. So you release the bottom material, so the material will bulk up, okay? So if the material is strong enough, they will not bulk up. If the material is not strong enough, it will bulk up. So you want to find out how much stress built up inside the structure. So one way is by design different kind of structures with different lengths and different width, okay? So for longer, you can consider you have a longer beam. So the buckling stress will be smaller. You have a very long, like a ruler. Do you have a ruler? Yeah, may I borrow the ruler, please? Yes. It's a very thin structure, right? So you push the top and the bottom, give a compressed stress, you can see the buckling easily, right? But for ballpoint pen, do you think it will be easy to buckle? No, not at all. Even using my fourth chance, I cannot make the buckle. So the same idea, you can design, thank you very much, different kind of cantilever beam with a different thickness and length. For shorter length, it's harder to buckle. For longer beam, easier to buckle, okay? It's the same idea, wider beam, harder to buckle, thinner beam, easier to buckle, okay? So now we go to this structure. So you can see there are several different kind of lengths of structural designs cantilever beam. So for this portion, the length is 150 micron, and then 200 micron, then 250 or 300 micron. So the length is increasing in this direction, okay? And also the width. The width, as you can see, this one is a widest one, then and you can see the smaller, the thinner ones on the other side. So the width is also decreased from this side to the other side. Okay, so you can imagine. So the whole different structures on the right-hand side. The right-hand side material is easier. Structure is easier buckling than the left-hand side one because it's longer, right? And the bottom one is easier to buckle than the top one because the bottom one is thinner. Okay, the top one is wider. But when the beam buckling up, when you look from the top to the bottom, how do you know it's buckling? Because it looks the same, no differences. Okay, so the way to tell is buckling or not from the top, you can shine a light, monochrome light, onto the surface, monotone light. For example, like a green light. Okay, one spectrum light, one wavelength light onto the surface. So the light onto the surface, okay, if the surface is flat, you won't see any diffraction pattern. But if it's buckling up, because of deflation coming out from the surface. You start to see a lot of Newtonian ring. Do you see the Newtonian ring? A lot of these things, Newtonian ring. So the Newtonian ring, you can count the number. So the difference between two Newtonian ring, the distance is 1/4, as I remember, 1/4 of your wavelength. So you can count the number to count the height variation. Okay, how much buckling, how much micron you buckle up. So you can count the number. For example, you have a 10 Newtonian ring. So the wavelength is like a 400 micron. So you got a 400 divided by 4 times 10. You got a 1 micron buckling up. Do you understand? Okay. So the distance here, you can count on how many Newtonian ring you can visualize from the top. Each Newtonian ring, the distance is 1/4 your wavelength. Okay, 1/4 wavelength. So you count 10 of them. So that means the distance from here to here is 10 times 1/4 of your wavelength lambda. Okay, so by using this method, you can quickly to understand. Okay, at what kind of structure, you can see from the structure here. So here is okay, you can see the boundary here. For those structure here is flat, right? No Newtonian ring. The center one, 2 micron one, you can see 2 without Newtonian ring. The other two thinner ones start to have a Newtonian ring. And on this one is a longer beam. All of them have a Newtonian ring. So starting from this point, the beam start to buckling. Okay, so we can use this as a critical structure. It's a critical structure. So using this structure, and you can plug into back the critical buckling stress for this kind of beam, and you can recalculate what kind of compressed stress encountered inside the beam. You can do the calculation easily. Understand? This is for compressive stress. Okay, so you find the one cantilever beam which can bulk up, and try to find the minima, the thickest beam you still can bulk it up. Okay, the strongest beam you can still bulk it up. That's the boundary condition. So using this boundary condition, you know the geometry of the beam, so you can do the calculation about the critical stress. What's the kind of critical stress is inside the beam? So this can be applied to all the material. We assume all the material has the same compressive stress. So at some kind of critical point, critical structure, it starts buckling. Okay, so from the structure, the array of the structure, you can find out which one is a critical structure. Okay, this is for compressed stress. Okay, however, you want to use it in the same idea to measure the tensile stress. Is it possible? For compressive stress, you can get a beam buckling. For tensile stress, can you see the buckling? No, always flat. So I want to use the same idea to measure tensile stress. How do you do? Okay, some smart guy. Harry Gacko, he found it this way. Okay, so originally we have a compressive stress, right? So we push in this direction, right? We want to do the compressive stress. Let me write it down. So we have a compressive stress in this direction. Okay, for example. Okay, compressive stress in this direction. So the beam will bulk up. However, we want to use this idea to do the tensile. So we rotate the cantilever original in this direction into vertical direction. Okay, so we put this cantilever, the beam structure inside a ring over here. So when you push the ring here, so the top and bottom will be extend, right? Right? So vice versa. So when you have a tensile stress here, the top bottom will be compressed. Right? So using the ring structure and rotate the beam by 90 degrees, so you can have an upside stress from this beam to the other two beams. So here, if you have a compressive tensile stress on the surface, using the ring structure, you can reverse this kind of stress onto the vertical beam. So the vertical beam still have a compressive stress. So you can use the same strategy as before, the buckling strategy, to understand how much compressive stress is applying here. So the compressive stress applied here is the same as the tensile stress applying on the side. The magnitude is the same. The difference is in this direction is compressive, other direction is tensile. Okay. So this ring we call the Gacko ring. So you can see the Gacko ring structure. So when these two sides are pulling outside, pulling outward, so the center two part will be pushed in. So we can transfer the tensile stress in the vertical direction, become compressive stress again. So the compressive stress you can use in the above mentioned Newtonian ring method to measure the buckling status. Okay. So if you have a very long structure, the stresses not only those the above two methods we are doing here is by measuring the uniform stress. If the stress is uniformly distributed inside the beam, you can use these two methods to measure. However, the stress is not always uniform, as I mentioned. There will be some gradients along the surface, okay, along the vertical surface. So that's why finally you will see the beam curving up, right? If the stress is not that high, if the beam is not long enough, you won't see much curving up. So if you want to extend the beam, it's not easy to extend the beam to become a very, very long beam, right? It cannot survive at all. So the other way is by to spiral, to make the beam become a spiral structure. So for the spiral structure, you still have a very long beam, but you rotate along the center, become this kind of like a clip structure. So for the clip structure, if the structure is curving up, that means if the beam is curving up, so you will see the boundary position is higher than the center one, become like a ball structure. So from the ball structure curvature, you can find out how much displacement from the tip to the center, and then finally you can get the stretch gradient inside the beam. Okay. So if the gradient is downward, you will see is upside down ball. Okay, the structure will be upside. Okay. Yeah. So that's using the very long beam to measure the stretch gradient. The uniform stretch gradient. Once you have a gradient, you can see the ball up, the ball down. Okay. Okay. And also you can using different methods by using laser or using indentation method to measure the Young's modulus of the beam, spring constant of the beam, or using the dynamic way to measure the resonant frequency. There's a different kind of tools you can use. And you want to measure the stiction, the connection of two beams. You can use in this Bosch method using apply pressure along this membrane. So we have high pressure on the bottom, low pressure on the top. So you can deform this kind of membrane, or even peel the membrane from the surface. In that case, you can see the adhesion force between two material, or using this Bosch structure, you still can measure the Young's modulus or the stress inside the beam as well. So a lot of things information you can get from these Bosch methods by using apply different pressure along these two different sides of the membrane. Okay. Okay, so finally, I give one example for surface micromachining. So you can fabricate a rotational electro motors. This is the first electro motor fabricated by UC Berkeley, Professor Yuchong Tai and Professor Longsen Fan. Okay, so this structure is based on 2 polysilicon and the 2 superficial layer process. Okay, so here shows you the detail of the process. So you want to this is a cross section of the structure. So you can see the device consists of the rotor. The center part is a rotor. So the rotor is anchored by using the bearing. Okay, the center part is the bearing. The bearing is anchored at the center, and the rotor rotates according to the bearing. Okay, and the outside we have a stator. So the stator is those part are the stator. So this is a rotor, and the center part is the bearing. Okay, so the rotor will rotate above the bearing, and the stator will give electrostatic force to attract the rotor to rotate along this direction or the other direction. So this is electrostatic motor. So on electrostatic motor, so the moving part is this part, the rotor part. The stator and the bearing, they are fixed structures. Okay. And also you can see the rotator here. The rotator here also has several dimps. That means the extrusion structures underneath. So on the top, you can see a dimp structure on the top. For example, like a small hole here. So in a small hole here, underneath you can see the extrusion structure. The purpose for the extrusion structure is try to reduce the contact area between the rotor and the bottom surface. So by reducing the contact area, you can reduce the friction force. Yeah. So in micro scale, as we can remember, electrostatic force is second order, right? L2, L cubic, L square force, right? It's proportional to the surface area, the electrostatic force, and also the friction force is also a surface force as well. So they are equal in the micro scale. So if you don't try to reduce the friction force, the friction force will be the hurdle to allow you to move the structure by using electrostatic force. Okay, so it's important how to control the friction force as small as possible in order to allow the electrostatic force large enough to move the structure. Okay, so here they design a dimple, a small things, we call it dimple, extrusion things on the bottom. Okay, so here shows you how to use in 2 polysilicon structure. So one polysilicon structure has been applied to fabricate the rotor and the stator. The second one has been applied to the bearing system. So here shows you some process. So after the first polysilicon deposit onto the first superficial layer, then you deposit the second superficial layer, then the bearing part. After you take out the 2 superficial layer, you got the rotor and the stator. So the rotor and the stator is fabricated at the same time when you see the cross section. So the rotor and the stator are fabricated by using the first polysilicon layer. So the center part is fabricated by the second polysilicon layer. So between these two, there are 2 superficial layers. The first superficial layer is under the first polysilicon. So after the first polysilicon deposition and the pattern, the second superficial layer deposit onto the first polysilicon layer. Then we bring the second polysilicon layer as a bearing. So after the end of the process, take out all the superficial layer, you got the rotating, freestanding, free rotating the rotor part, released from the structure. Okay, so several key things are, there's the first generation. Actually, they have several generation. You can, maybe in the homework, we can give you the second generation. and try to consider how to fabricate the second generation is even harder. Because as I mentioned, friction is the problem. So in the first generation, they're using dimple to try to solve a little friction problem. However, there's still some interface between the rotor and the bearing, right? When you rotate, the center part will contact with the bearing. So that part also gives a lot of friction. So how to reduce that part of friction? Okay, in the second generation, they deposit some silicon nitride. Silicon nitride fin is better resist the friction and also give a less friction force. So they will bring some silicon nitride fin between the bearing and also your rotor part. So the structure is a little bit different from this one. So in the homework, you will see the structure and try to find out the fabrication process. Yeah, to accomplish that kind of structure. Okay? So this gives you an example. Yeah, just so I think this practice is important because in the future you are going to design different type of devices. So starting from this point, you need to learn how to bring up the idea step by step for the fabrication to allow people to understand what's your fabrication process. So it's important for you to know how to drill down the process flow step by step. So you need to show the detailed process for like the lithography steps. You just bring up the important part. For example, like the structure change. When you apply different mask, the structure will change after you apply in the mask process. So you need to show each important step. That means the structure change steps. Okay. So for example here, actually the process is quite complex. If you want to finish the process, you need to spend like around 100 steps. But we don't have time to draw all the steps at the same time. So we just are using few view graphs to review important steps. The important steps including you deposit new fin, you do the patterning, and then you do different structures, those kind of things. So the process will be a little bit more complex than this one. This is too simplified, actually. You can see a lot of process has been merged into one on this one. There are already 5 processes over here. But for you are the beginner, so you don't draw this kind of simplified things. You can draw a little bit more complex, but you don't need to do this in much more detail. You just need to bring up the important part. For example, the structure change, material change, those kind of things. Try to do some practicing in your homework. Okay. We will see you in the next homework. Okay. Okay, I think this is the last transparency.